And that's what we're digging into today. We have this transcript from Metabolism Made Easy that breaks it down.
The 3 stages of catabolism.
Yes. And the mission for this deep dive isn't just to list the steps. I think most of our listeners probably remember the basics from biology class. We want to understand the why behind the architecture. Why does the body move molecules across certain membranes? Why are some reactions isolated in the mitochondria while others aren't?
That spatial organization is everything. It's key. Biology isn't just about the chemistry, it's about the geography. Where a reaction happens is just as important as the reaction itself.
So let's trace the journey. We're going to follow a food molecule from the moment it enters your gut until it literally powers a thought.
Or a muscle contraction.
And the source material divides this into 3 distinct stages. So stage 1, it calls the great breakdown, happening in the intestinal lumen.
Right. And for this audience, we don't need to, belabor the point that proteins become amino acids or that polysaccharides become glucose.
Everyone knows that.
There is a nuance in stage 1 about fats, triacylglycerols, that I think often gets glossed over.
This is the part that actually caught my attention. Because with glucose and amino acids, the logistics seem pretty straightforward.
They are.
You break them down, the enterocytes, the cells lining your intestine, grab them, and they just hop into the bloodstream. They're water-soluble.
They fit right in with the plasma. It's a free pass. But lipids are hydrophobic. They hate water.
Right.
So you have this basic engineering problem. How do you transport a fat-based fuel through a water-based system like your blood?
And the solution the body came up with is, well, frankly, it seems inefficient at first. We break the triacylglycerols down into fatty acids and monoacylglycerols in the gut, but we don't just ship those pieces out.
No. Once they get inside the intestinal cell, we actually reassemble them. We spend energy to put the triacylglycerol back together.
See, that's the part that feels counterintuitive. Why smash a Lego castle just to rebuild the exact same castle inside the next room?
It's a packaging requirement. If you just dumped raw fatty acids into your blood, they'd clump together or even damage the capillaries.
Okay.
So the cell rebuilds the fat and then wraps it in a special protein lipid coat. It effectively builds a submarine.
The chylomicron.
The chylomicron. It's a massive, well, relatively speaking, lipoprotein particle. It encapsulates the hydrophobic fats so they can travel safely through the blood and lymph.
So that inefficiency of rebuilding the fat is really just the price of admission for using the bloodstream.
Exactly. It's a necessary cost for safe transport. And that really concludes stage 1. We've broken things down, and in the case of fats, packaged them up, everything is now in circulation.